Oh, hello, everyone. We are live. Thank you, and welcome to MAA's Distinguished Lecture Series. My name is Kiera Edwards, and I'm the Director of Programs and Grants Management here at MAA.
And I'm Deirdre Longacre Smeltzer, and I'm a Senior Director for Programs with the MAA, and I also welcome all of you. We will get started with the presentation itself in just a minute, but I want to welcome all of you who are joining us. This is our 6th virtual distinguished lecture, and one of the great things about holding virtual events is that people can join us from all around the globe. So if you are if you're on YouTube, you should be able to see our YouTube chat. And if you'd like to, I invite you to drop in the chat where you're tuning in from. So as I said, we've got our 6th speaker this evening, a great presentation lined up by Dr. Naiomi Cameron, kicking off our fall series. This is the first of 3 great speakers we have for the fall season, including Dr. Ken Ono, who will be speaking to us just 2 weeks from today, and Dr. Della Dumbaugh joining us in November. So check those out as well in the upcoming weeks.
And we also have a lot of interesting things coming up in our MAA programs department. As most of you know, we have our fall virtual programming that's going to kick off next week. So please be on the lookout for that and sign up for a lot of great programs we have coming up. Some will include cryptography. Some will include closing the gap between high school calculus courses and instructor level calculus curriculum. We'll have a special virtual program for our math undergraduates. So please be sure to check out the schedule coming out next week. We would love to have you attend some of those. And we also have our open math workshops. Those are going to kick off next summer, but proposals for those are going to be due November 4th. So please sign up for those as well. It's going to be a great session for those who have some ideas of intensive courses they'd like to teach for professional development.
Yeah, absolutely. So there really are, one of the silver linings of the pandemic was that we really embraced a lot of virtual programming, and so along to supplement our in-person programming. So if you want to stay up to date with MAA programs in general, we have a weekly email giving you a heads up about whatever is on deck. And you can sign up for that and receive those each week in your mailbox, in your inbox. So with that, it is a few minutes past the top of the hour. So let's go ahead and get started with the program itself. Welcome again to all of you who are joining us for tonight's virtual MAA Distinguished Lecture. I am delighted that you're here for the event featuring Dr. Naiomi Cameron as our speaker. I'll just reiterate that the YouTube chat is available and will be seen by Dr. Cameron throughout. And in addition, we will be allowing time at the end of the presentation for some Q&A with Dr. Cameron. So don't hold back on your questions and comments as we are moving through the presentation. All right, and with that, I invite our Executive Director, Dr. Michael Pearson, to join me and introduce our speaker.
Thank you, Deirdre and Kiera. Great to be here tonight. And Dr. Cameron, so great to have you here to kick off our fall series. I see that we've got people popping up from all over the place in the country. I even see somebody from Barbados. So it's great to be able to have such a wide reach, a great audience for this event. And I'm looking forward to your talk tonight. So it's my job to introduce you a little bit. So just a little background. Dr. Cameron currently serves as chair of the Department of Mathematics at Spelman College in Atlanta. Now, if you go back quite a few years, Dr. Cameron's first nudge towards her lifelong journey with mathematics was in high school when her pre-calculus teacher recruited her for the math team. But that nudge wasn't quite enough. In fact, she has related that her first visit to the math department when she matriculated to Howard as a freshman was to try to use her AP credit to get out of taking any more math. So we all owe thanks to the Howard University faculty who encouraged her to stay in mathematics and ultimately to major in mathematics, where she completed her undergraduate degree at Howard in 2002. She went on to get a PhD in mathematics, in 1995, undergraduate, and went on to get her PhD in 2002. Prior to joining Spelman in 2019, Dr. Cameron served on the faculty at Harvey Mudd College, at Occidental College, and at Lewis and Clark College in Portland, Oregon, where she also served as Associate Dean for Faculty Development. Dr. Cameron learned from her own experiences the importance of mentoring and encouragement for her students and colleagues. We are all grateful for that. She shares her love of mathematics through teaching undergraduate courses, mentoring undergraduate research experiences, and a variety of professional activities. According to Jenny Quinn, MAA president, you can tell a lot about a person by how they handle roadblocks. When frustrated by a lack of mathematical progress, Naiomi urges us to write up what we do know, and in the process, we move past the barrier together, sometimes in the same directions, sometimes in a new one. She is a fantastic person to have as a collaborator. And Naiomi, we are delighted to have you join us this evening. Thank you so much.
Thank you, Michael. What a great introduction. Thank you so much. Welcome, everyone. I'm just really happy to be here and to share with you a little bit of my story. And I appreciate Michael introducing me so well and actually foreshadowing some of the things I'll talk about. So my goal in this lecture is to tell you a little bit about my journey in mathematics through my relationship with this mathematical object known as the Riordan group. And along the way, I'll share some messages that I hope will be useful to especially students who may be in the audience and at the beginning of their mathematical journeys, or my many colleagues out there who are further along in their journeys, but still discovering. So the talk will proceed in 3 parts with a conclusion. So the first part, I'll tell you a little bit about myself, and we'll need to talk about sequences and generating functions in order to talk about Riordan arrays. So I'll tell you how I got to know these objects. And then in the second part, we'll show some examples that illustrate these objects that we're going to study. And we'll look at a couple of combinatorial problems to which Riordan arrays can be applied. And then finally, we'll close with some messages and some lessons, we hope. So when we think of mathematics as a human experience, I think we all realize that every mathematical journey starts in childhood. So when I was a kid growing up in Providence, Rhode Island, I certainly did not dream of being a mathematician. For the most part, mathematics to me was just like every other subject where my parents, encouraged me to study and do my best and instilled a certain expectation that I should try to excel where I could. So when I got to middle school and high school, I began to develop a stronger affinity for mathematics. And I think what I was doing is sort of realizing that mathematics was a way of making sense of the world. And for me, at that time, I found the order and structure and predictability of math comforting. So I found a certain level of comfort in that. So I went to Howard University, as Michael said, and I did indeed try to get out of taking mathematics. And that's because I went to Howard University, which is an HBCU, which has an engineering school and an architecture program. And I had every intention of becoming an architect. And I think what I was thinking at that time is that my appreciation for structure and order I wanted to somehow marry that with my interests in art and creativity. And to me, you know, architecture seemed like a good place to do that. But eventually, thanks to my faculty members at Howard University in the math department, I was drawn away from architecture and more towards mathematics. And they really encouraged me to pursue graduate school in mathematics, which I did. And that was where I was introduced to combinatorics and to the Riordan group by my advisor, Dr. Lou Shapiro. And he was the first person to, with his collaborators, write about the Riordan group in 1991. So for those of you who may not be that familiar with combinatorics, I wanted to say a few words about it. So unlike other areas of mathematics that focus primarily on continuous phenomena, combinatorics is the branch of mathematics that is most concerned with counting, analyzing, optimizing, classifying in some way systems of discrete objects. So it draws upon many other areas of math, including algebra and number theory, geometry, topology, analysis, probability and statistics, you name it. And its applications outside of mathematics range from computer science to physics, chemistry, biology. There's lots of ways that it can be applied. And one of the things I really enjoy about combinatorics is its versatility in terms of applications, and also the fact that it can't really be separated from the other areas of mathematics, no more than you can separate the sand from the ocean. So when I was introduced to Riordan arrays in graduate school, it was really the first time that I felt genuinely creative as a mathematician. So in order to talk about Riordan arrays, we'll have to talk about sequences and generating functions. So let's try to illustrate those things with a couple of examples. So let's start with our first counting problem, which is a classic tiling problem. And the question is, how many ways can you tile a board? And the board is going to be 1 by n, using 1 by 1 squares, which I'll color red, and 1 by 2 dominoes, which are going to be colored blue. So if n were 1, we just have a 1 by 1 board, and we can place 1 square on it, and that's the only way it can be done. If our board is 1 by 2, then we could cover it with 2 squares, or we could cover it with a domino. So there's 2 ways to tile this 1 by 2 board. If n equals 3, we can tile the 1 by 3 board with 3 squares, or 1 squared followed by a domino, or a domino followed by a square. And if n equals 4, there are 5 ways to do it, which I've depicted here. So far we have a sequence that starts 1, 2, 3, 5 for the number of tilings that we have in each case. So here's a question for the audience. And this is a question really just for the students in the audience who may be out there. How many ways can we tile a 1 by 5 board? So I'll give you a second to answer. And I've been told that there's a bit of a delay potentially with the comments. So I'm going to give it a second here to get some answers. How many ways can we tile a 1 by 5 board using squares and dominoes? Is anybody out there able to draw them up real quick? If you haven't done this problem before, or if you remember this problem, perhaps from a class or some other experience. Okay, great. I see Shada Khan says 8 ways. Awesome. Great. That is correct. There are 8 ways to do it. I did not draw all 8. I ran out of time to do that. But there are 8 tilings of a 1 by 5 board. And for a 1 by 6 board, we would have 13 tilings. And for a 1 by 7, we'd have 21. And for a 1 by 8, 34, and so on. And so we see that we're getting a sequence, which is counting, the number of ways that we can answer this question. And this is actually the Fibonacci sequence, which we all maybe are familiar with. So let's talk a little bit more about why we're getting the Fibonacci sequence. So let's let Fn be the number of ways that you can tile a 1 by n board using squares and dominoes. So one way to think about this is when we tile our board, we're either going to start the tiling with a square, And then we'll have a 1 by n minus 1 board that we have to tile in fn minus 1 ways. Or we're going to start our tiling with the domino, and we're going to tile the remaining board in fn minus 2 ways. So the number of ways to tile the 1 by n board is equal to the number of ways that you can tile the n minus 1 board, plus the number of ways that you can tile the n minus 2 board. And so we get our classic Fibonacci recurrence formula, which says that each term in the sequence is the sum of the previous two. And we can think about what would happen, I suppose, if n were 0. In that case, the collection of tilings would be empty. And so we'd have the empty set, and there's only one empty set. And so it makes sense to define f0 to be 1. And that's how we get our initial conditions for our sequence. So we all are probably somewhat familiar with the Fibonacci sequence. One of the things I want to point out about it is that it's pretty special for a number of reasons. For one thing, it actually is not just a mathematical curiosity. It actually shows up in the world, and it describes, some really interesting patterns of growth in natural objects often, and in objects that are often considered beautiful. So the Fibonacci sequence is special for that reason, but it's not that special because there are actually lots of other very interesting sequences out there that describe other types of phenomena, and in combinatorics, we like to study them. So one challenge with working with a sequence is that it's an infinite list of numbers, and carrying around an infinite list of numbers can be cumbersome. So what we do in combinatorics is we often find it useful to package our infinite sequence into something we call a generating function. So what is a generating function? What a generating function is sort of a function that we associate to our sequence. So given a sequence, its ordinary generating function, or OGF for short, will be a formal power series where the nth term in the sequence becomes the coefficient of x to the n. And then we sum up all of our powers of n. So in other words, we take our infinite list of numbers as a sequence, and we turn it into an infinite sum. So you may be wondering, why is that useful, or how is that better? So to show you how this can be useful, let me just illustrate the Fibonacci generating function. So we're going to show how this sequence can be packaged in its generating function. So let's go back to our tiling problem, and let's call our generating function for the Fibonacci numbers capital F. So to each term in capital F, we are going to associate a tiling that term is counting. So for instance, the term 1x to the 1 is corresponding to the one tiling we get when we have a 1 by 1 board. And we can actually kind of just associate each of our squares in the tiling with an x, and associate each of our dominoes in the tiling with an x squared. And for instance, when we look at the case where n equals 2, we see that we have an x times an x and an x squared, and together that gives me 2 different tilings for a total of 2 times x squared. So each term in our generating function can be associated with a collection of tilings. And we can sort of associate each of the tiles with x or x squared, depending on whether it's a square or a domino. So because we're tiling a 1 by n board, each tiling can be associated with an x to the n. And the coefficient of x to the n is going to be the total number of tilings of our 1 by n board. So again, how is that better? How is this infinite sum more useful than the infinite list? So we can actually look at this a little differently. So we can do a little algebra here. So let's take our Fibonacci generating function and let's multiply it by x. And you can see what happens. All the power is increased by 1. Then we're going to multiply our Fibonacci generating function by x squared. You can see what happens. The power is increased by 2. And now when you add x times f to x squared times f, you get a series, a formal power series, that looks almost exactly like f, except it's missing the first constant term. And so what we're finding here is that if we take x times f plus x squared times f, we get f minus 1. Or in other words, we have f is equal to 1 plus xf plus x squared f. So we have a formula for f that we can solve, and that will give us what we call a closed form for the generating function. So I just want to point out that there's another way to have gotten to the formula at the top of the page without having to do the algebra we did before, which is you can sort of think about all of our tilings, which are counted by f. They all are either the empty tiling, or they're a tiling that starts with a square, or they're a tiling that starts with an x squared. And so the generating function for the tilings that start with a square is x times f. And the generating function for the tilings that start with a domino is x squared times f. And so that means these generating functions have to add up to f. And of course, the generating function for the empty set is 1. So that's just kind of a cool little trick that when you work with generating functions a lot, can save you some time. But in any case, we are now able to solve our equation for f, and we have what we call a closed form for the generating function of the Fibonacci sequence. And this generating function contains like all the information about our sequence that we need to know. It's all packaged in there. So one thing I would point out to those of you who are out there who have taken Calc 2, the students in particular, is that if you had been asked in your calculus class to write out a Taylor series expansion of 1 over 1 minus x squared, and you do the exercise of that, the coefficients in that Taylor series, centered at 0, would actually turn out to be the Fibonacci numbers, which is kind of remarkable because we kind of came to that conclusion without having to do any calculus or differentiation at all. So pretty cool. Okay, now that we have a little bit experience with sequences and generating functions, let's talk about Riordan arrays. And I'm going to kind of introduce us to Riordan arrays through a counting problem that that something like a Riordan array might typically apply to. So Riordan arrays come up a lot in lattice path enumeration. So here's a lattice path enumeration problem. So how many ways are there to get from the lower left corner of this grid at the start to the upper right corner at the end using unit length, north and east steps? So you can take a step to the right by 1 unit or a step vertically up by 1 unit. Those are the only steps that you can take. How many ways can you get from start to end? So one way to tackle a problem like this is to just take it one step at a time. Let's just count the ways that we can get to each point in the grid. So the points that I've labeled here, I'm labeling them with the number of ways that you can get to that point. So to each of those points, there's one way to get there. You can either take a north step or an east step. There's one path. Now to get to that point, there would be 2 paths because you could come from the 2 adjacent points and then take an east or north step to get to that location. So there's 2 ways to get there. There's obviously one way to get to these locations. There's 3 ways to get here, which is the sum of 2 and 1, the labels on the adjacent vertices, and so on and so forth. So at each point, the number of ways to get to that point is the sum of the 2 adjacent labels. So we just kind of we keep going, we fill it in, and we finally get to the end, and we find that there are 924 paths from start to end. So if we take the entries in that grid that I just drew, the red numbers, and rotate them 90 degrees, we see what we have is something familiar called Pascal's triangle, which we may all have had some experience with, perhaps as early as childhood. And, we know and love this triangle. It has ones on the exterior. The interior entries are obtained by taking the sum of the entries that are adjacent in the previous row. And there's also a formula for the entries of Pascal's triangle. They're known as the binomial coefficients, and there's the formula, the striking formula there for the entries of this array of numbers. So Pascal's triangle, again, it's very well known, and it's very pattern rich. So it's been known for at least 10 centuries. We use it for all kinds of things. We can use it to expand a binomial expression. We can use it to find really interesting patterns. So one of them is that the shallow diagonal sums of Pascal's triangle give you the Fibonacci numbers. So there's a connection there. And then if you were to just look at the odd entries of Pascal's triangle, they form this fractal pattern known as Sierpinski's triangle, which is pretty amazing too. So it's sort of an interesting question. Why is this seemingly simple array so rich with patterns and so ubiquitous? So to look at Pascal's triangle in a new way, let's left justify it. And let's think of every column as an infinite sequence to which we can associate a generating function. So I'll leave it as an exercise to the students to verify these generating functions for these sequences that you see on the screen. We see that the generating function for the first column is 1 over 1 minus x, which is our famous geometric series, and so on and so forth. But what's interesting about this sequence of generating functions is that it has the form of a geometric sequence. So that is, each term in the sequence of generating functions, that is, can be expressed as g times f to the power k, let's say, where g is 1 over 1 minus x, and f is x over 1 minus x. So we have this geometric sequence of generating functions, which has just this initial value that you start with, called g, and then a common ratio, f, which is the constant ratio between all of the successive terms. So that's going to lead us to our definition of a Riordan array. So what is a Riordan array? It's an array that has the similar properties to Pascal's triangle, in that it's an infinite array in which each column has a generating function, and the sequence of generating functions for the columns forms a geometric sequence. Now, there are some conditions that we have to have on G and F, which I won't get into all the details of. But in many cases, what we're going to have is our Riordan array will be lower triangular because the constant term will be non-zero for G, and the constant term for F will be 0. So typically, we're going to be looking at an infinite lower triangular array in which the generating functions for the columns form a geometric sequence. So Pascal's triangle is a Riordan array. And because by definition, the columns form a geometric sequence, we really only need to know what the initial function is and what the common ratio function is. So we can kind of shorten our expression for our Riordan array by just the ordered pair of those two generating functions. So here are some fast facts about Riordan arrays. First of all, the invertible Riordan arrays form a group under matrix multiplication. And that matrix multiplication actually can be encoded in terms of the generating functions, and that's the first equation you see on the screen. Don't worry about that too much. I won't make you memorize it, but there is an operation that you can perform using that expression. And that multiplication is the same as matrix multiplication. We can also have our Riordan arrays kind of act on a sequence. So that's kind of the expression you see at the bottom of the screen in red, where we have a Riordan array times a sequence. And by sequence, I mean generating functions. So I may use them interchangeably sometimes. So you have your Riordan array times a generating function, and you use that operation that's indicated at the top of the screen to get your output generating function. And Riordan arrays, because they form a group under the right circumstances, they really can be used to study and discover combinatorial statistics and identities. And that's what I'll try to show you more of in the rest of the talk. But for every algebraic observation that you can make in the Riordan group, I would say that it usually begs for a nice combinatorial or bijective interpretation. So it's never really the end of the story when you're dealing with, Riordan group results. So just to show you a couple of neat tricks you can do with Riordan arrays. So if we take our Pascal's triangle and we multiply it by the sequence of all ones, and the generating function for that is sort of indicated in gray below. So if we perform the Riordan multiplication, the result is the sequence of powers of 2. And so that's a result that's consistent with what some of us may recall about Pascal's triangle, which is that the row sums give you the powers of 2. Another cool thing you can do is if we took our Riordan array in the form of Pascal's triangle and we kind of shifted the columns down by changing the common ratio function to x squared over 1 minus x, and then sum the rows, we get the diagonal sums of Pascal's triangle. And as I indicated earlier, that would give you the Fibonacci numbers, and that can be proven using the Riordan group algebra. So you can also, in addition to verifying things that you may already know using the Riordan group, you can also discover some not so familiar identities using the Riordan group. So here's just one example of a result that appeared in a paper that I wrote with my collaborator, Asamawa and Quanta in 2006. And we were able to use the Riordan group to show this kind of crazy looking identity, but very cool. Okay, so now that we have a sense of what the Riordan group is, let's look at a couple of counting problems where Riordan arrays can be applied. So let's try a triangulation problem. So the question is this: how many ways are there to divide a polygon into triangles? So let's look at the case of a pentagon. So if you take a regular pentagon and you want to divide it into triangles, it turns out that there's 5 ways to do that. And this kind of question might be relevant and is relevant in many cases in problems like computer imaging. So there are 5 ways to divide a regular polygon into triangles. And it turns out that if you go to a larger polygon, say a hexagon, a regular hexagon, there's 14 ways to do it. And I didn't draw all of those possibilities for you this time. But the number of ways that you can triangulate a regular polygon in general is given by the Catalan number sequence. And this is a famous sequence that many people may know, but may not have, sort of the same popularity, let's say, as, say, the Fibonacci numbers. So before we discuss the generating function for the Catalan numbers, because you shouldn't just believe me that it's the Catalan numbers, we should be able to show that we're getting a certain generating function to answer this question, which we'll do in a second. I actually want us to think about a question that goes beyond just counting. So what if, in addition to counting these objects, we also wanted to somehow classify or group them, or sort of tell the difference between them somehow? They're distinct objects, like what makes them different from each other? So for me, when I look at these particular objects, they all look pretty similar to me, and it's hard for me to distinguish them. So just to mix things up, let's convert these objects into something different, and might be more familiar, perhaps, or might just be somehow easy to work with. So what we're going to do is we're going to turn our triangulations into binary trees. So I'll kind of walk through how we would do this. So at the bottom edge of our pentagon, we're going to kind of plant some grass and plant a seed and designate a root at the bottom of our pentagon. And from that root, we're going to have 2 branches that come out, and I should use the word edges, 2 edges that come out of the root, and each edge will touch the remaining sides of the triangle that it's in. And then we're going to go to the next adjacent triangle and perform the same procedure. So from the edge to which we have reached, the edge of the triangle that we have reached, so at the yellow line, we're going to branch into two edges that reach the remaining sides of the triangle that we're in. So hopefully you can see that okay. So that's how we're going to get our binary trees. So I'm going to redraw the trees and stand them up a little straighter so that you can see them a little better. And there they are. There are 5 binary trees that correspond exactly to our 5 triangulations. So what I just described is a bijection. I won't give a formal proof of that, but it's a pretty well-known bijection, and so I encourage you to go and look it up if you are interested. So instead of counting triangulations, we are going to count binary trees, and we're also going to think about like how to classify our binary trees, like how to sort of measure the difference between them. So let's see, I think we can go to the next slide here. I just want to mention one other thing about our binary trees, just so that it's clear what we mean by a binary tree. These trees are rooted at the bottom, so that's why I've starred the root node. Okay, so that's a distinguished node. And then at each node, we branch upward with 2 edges coming out, or for the non-root edges, for the non-root nodes, we may have no edges coming out of it. So each node has what we would call out degree 2 or 0. And that's kind of what makes it a binary tree. Okay, so we're going to first count our binary trees using a generating function. So let's let C denote the generating function for the number of binary trees. And we're going to use our principles from earlier in our work with the Fibonacci generating function. And we're going to think about what every binary tree has to look like. So every binary tree has 2n edges. And if n is 0, that's just the empty tree. Otherwise, the tree is non-empty. It has a root with 2 edges coming out of it, a left edge and a right edge. And to each one of those edges, we can attach another binary tree, each of which can be counted in C of x ways. And note that the trees that we're attaching could possibly be empty. So looking at that picture, what we have is that the generating function for all binary trees, C, should be equal to the generating function for the empty tree, which is 1, or that is plus the generating function for the non-empty trees, which according to our picture would be C squared times x. And I want to note that we're associating an x with each of our right edges in the same way that we did above for the 5 trees that we saw. Okay, so n here in our generating function is corresponding to the number of right edges that we have overall in our binary tree. So with this formula for C, we can now solve for C and get a closed form for the generating function, and there it is. The coefficients in the expansion of 1 minus root 1 minus 4x over 2x will give you the Catalan numbers. So we've successfully counted our binary trees. Now, let's think about the other question I asked, which was how to classify these trees. Like, how would we measure the difference somehow between these trees? So when we look at these trees, there are some things we might notice. Some of them maybe lean more towards the left and some lean more towards the right. So there are probably lots of ways to measure this, but one way would be to count the number of nodes on the rightmost branch of the tree. So for larger trees, it might be interesting to know, like, how many of our trees, have a certain number of nodes on their rightmost branch. Or how is the number of nodes on the rightmost branch distributed over our entire set of trees? So at least for our 5 trees here, with 6 edges, we can at least indicate how many nodes we have on the rightmost branch. So I've indicated those in red. We have 2 that have 1 node on the rightmost branch. We have 2 more that have 2 nodes on the rightmost branch, and we have 1 that has 3 nodes on the rightmost branch. And so in general, if we wanted to kind of, compute our, let's call it a statistic, because after all, a statistic is just, a value that you want to compute on some sample. So in our case, the sample is binary trees, and we want to compute the number of nodes on the rightmost branch. So for this statistic, here's what we would have in terms of a summary, at least for n equals 0 through 5. And so this is an interesting array of numbers. And it turns out that this is a Riordan array. So I claim that this array is the Riordan array with the initial value 1 and the common ratio x times c, where c is the Catalan generating function. So how do I know that? I mean, you can't just go by like this limited evidence you see on the screen. How do you know that that's actually true? So let's think about that. What we would have to do is we would have to think about the ordinary generating function for the number of binary trees with a certain number of nodes on the rightmost branch. So for instance, let's say there were no nodes on the rightmost branch. Well, the only way that can happen is we're talking about the empty tree, and there's the generating function for that. It's 1. If we had 1 node on the rightmost branch, then our tree would kind of look like this, a root with 2 edges coming out, a left and a right edge. And then we could have a tree, possibly empty, attached to the left edge. And so the generating function for that is x times cx. If we had exactly 2 nodes on our rightmost branch, we'd have a picture like this, with generating function x squared times c squared. If we had 3 nodes on our rightmost branch, then our tree would look like this. And in general, what we see is that the generating function for the number of binary trees with exactly k nodes on its rightmost branch would be x to the k times c to the k. So when you look at this sequence of generating functions, you should recognize that this is in fact a geometric sequence with an initial value of 1 and a common ratio of x times cx. And so that's my proof, in quotes, that the number of binary trees having k nodes on the rightmost branch is given by the following Riordan array. So that's cool, but what else can we do with that? So here's something interesting. We've kind of summarized this statistic in a certain way. We can actually compute the average number of rightmost branch nodes among our binary trees. So the way that we would do that is we would take our Riordan array, our 1, xcx, and we would multiply it by the sequence of non-negative integers. And that product would give me the total number of rightmost branch nodes among all of my trees for each n. So that's a sequence, and I actually have the generating function for that sequence based on the Riordan group algebra. And so what I can do is I can take the nth term of the generating function that's counting the total number of rightmost branch nodes, take the nth term of that and divide it by the number of binary trees, which is, of course, the nth term of the Catalan generating function. So we have to use some extraction methods that we have in combinatorics, which we do. So there's a little work involved there, but we can show that, that this quantity actually approaches 3 as n goes to infinity. So the number of rightmost branch nodes approaches 3 as the number of edges in your binary tree approaches infinity. Okay, so let's look at one last illustration of how Riordan, the Riordan group and Riordan arrays can be applied to problems and combinatorial identities and combinatorial statistics. So I want to take a look at our binary trees, and I'm actually going to convert them to paths now. I said earlier that a lot of Riordan group problems are related to lattice path enumeration problems. So it turns out that each one of these binary trees can be converted to something we call a Catalan path. And a Catalan path is just a path that starts at the origin or on the x-axis, and you can use unit up steps of slope 1 and unit down steps of slope -1. And you have to land back on the x-axis, and you can never go below the x-axis. So that's how we define a Catalan path. And so if our Catalan path had length 6, that is 6 steps in it, there would be 5 ways to have a Catalan path like that. And there is a bijection from the trees above to the Catalan paths below, which I won't describe right now, but happy to talk about it later if there's interest. And our rightmost branch nodes from our trees actually correspond to what we call returns on our Catalan paths. So a return is a point on the x-axis that's not the origin point of your path. Okay, so it's a point at which the path returns to the x-axis from its initial starting point. So one might ask questions like, well, what's the average number of returns among our Catalan paths? And of course, we've already answered that because we answered it for binary trees. And so we could just state right away that the average number of returns among our Catalan paths should approach 3. But there might be other things we want to study about these paths. So I'm going to give you another example of something we could look at to sort of tell the difference between these paths. We might look at things like how many peaks we have, or how many valleys, or in particular, let's look at the number of peaks that we have at height 1. So I've indicated those in blue on the screen. So we have 2 paths that have no peaks at height 1. We have 2 paths that have 1 peak at height 1, and then we have 1 path that has 3 peaks at height 1. So we're going to call the paths, the peaks at height 1, there's a term for them, we're going to call them hills, okay? So if you wanted to count hills among Catalan paths in the same way that we looked at rightmost branch nodes, you could. And it turns out that the number of Catalan paths of length 2n that have k hills is given by this Riordan array here on the screen, which is defined in terms of another famous sequence known as the fine number sequence. And in a not so recent now, I guess, but feels like it was yesterday, a very good friend and collaborator of mine, Jillian McLeod, and I wrote a paper in which we showed that the number of hills among our Catalan paths of length 2n has an expected value of 1, and the distribution approaches a negative binomial distribution as n tends to infinity. So that's super interesting. Now, I will just pause here and say that the fact that we expect a value of 1 for the number of hills among our Catalan paths does sort of beg for a bijective or combinatorial interpretation. And I'll just put a pin in that and maybe come back to it later if I have time. So something else you might look at with our Catalan paths is just the peaks, not just the peaks at height 1, but the total number of peaks regardless of what height they occur at. And it turns out that the number of Catalan paths of length 2n that have exactly k peaks is given by a famous array known as the Naiomi triangle. And the Naiomi triangle is actually not a Riordan array. It's not an ordinary Riordan array, at least in the way that we've defined it. And that's because if you actually look at the generating functions for the columns of this array, they don't form a geometric sequence. So I guess maybe this is a transition point where I would say that there are some limitations to the Riordan group, and none of the problems that we've discussed so far have to be solved by the Riordan group. Every mathematical device has its limitations. And I would say that after graduate school, when I moved away from home with my husband and my young family, I definitely started to drift away from the Riordan group. After graduate school, as Michael mentioned, I worked in California for a number of years and then in Portland for a number of years. And I encountered lots of new people and new experiences. And it made me think about exploring other paths and opening myself to other kinds of combinatorial problems and other ways of thinking about those problems. So I began to explore things like combinatorial determinants and Fibonacci tableau and permutation statistics and pattern avoidance, and even dipped my toe a bit into a little algebraic geometry with descends d'enfant. And I also experienced a lot of life changes, and building a career and a family comes with a lot of challenges. So in the face of all those challenges, as the Riordan group became less relevant to my work, it began to kind of recede and lay dormant in my mind as a tool for creative thinking. And so for the last part of my talk, I'm just going to say a few things about one last counting problem that came out of one of my more recent explorations, which was initiated completely outside of the context of the Riordan group. So the object of study here is called a linear chord diagram. So a linear chord diagram is a way of partitioning an even number of distinct objects into pairs. So if you had 4 objects and you labeled them 1 through 4 to distinguish them, you could pair the first 2 and the second 2, or you could pair the first and the third, and then the second with the fourth. And then finally, you could pair the first with the fourth and the second with the third. So there would be 3 ways to do it. So we represent these, sometimes they're called matchings also. We represent these matchings with a linear chord diagram, and the pairings are called chords, and so they're indicated with an edge that connects the 2 points, the 2 labeled points. And then the length of a chord is the distance between the paired objects, which are always labeled with positive integers. And then a chord that has length 1, we might refer to as a short chord. So here's a slightly bigger example of linear chord diagrams with 3 chords in them. And we can see that there are 15. And in general, the total number of linear chord diagrams with n chords is given by this fancy formula at the bottom of the screen, which involves factorials. So we're talking about much larger quantities in general, at least term for term, as compared with the Fibonacci sequence, for example. So for problems like this, when you're counting, linear chord diagrams or partitions or permutations, sometimes it's more useful to use what we call an exponential generating function. So an exponential generating function for a sequence is a formal power series, which has the form on the screen. And basically what it is it's an ordinary generating function for the sequence of terms we get by taking the nth term of our sequence and dividing it by n factorial. So in a way, it sort of like cuts down the sequence somehow and then, creates an ordinary generating function for the reduced sequence. So a quick example would be like for our linear chord diagram sequence, if you wanted to come up with the exponential generating function for that, you can do this quick little computation. You end up with the ordinary generating function for the central binomial coefficients with a change of variables of z over 2. And then you end up with 1 over root 1 minus 2z for your generating function. The exponential generating function, that is. So as usual, like maybe we want to look at these linear chord diagrams and somehow tell the difference between them. So we could sort of count them by the number of short chords that they have. So you can see that the purple diagrams have no short chords. The blue diagrams have 1 short chord. The green ones have 2 short chords, and the orange one has 3 short chords. So we've kind of divided it out that way. And so if you continue in that way, for all of your linear chord diagrams, this is the array that emerges. And so a good friend and collaborator of mine, Kendra Kilpatrick, we worked on a paper recently where we were very interested in finding a recursive formula for the entries in that array on the previous screen. And we wanted to generalize it in various ways. But one of the things we were able to do based on a recurrence that we found in the literature was we found an exponential generating function for the number of linear chord diagrams having exactly k short chords. And so here it is on the screen. But what's interesting now is that given this result about these exponential generating functions for the columns of our array, it turns out that our array, which counts linear chord diagrams by the number of short chords, turns out to be something we call an exponential Riordan array, which is that the kth column of this array has the form g times f to the k over k factorial, where g is the function that I've indicated at the bottom of the screen, and f is the function next to it. And it turns out that exponential Riordan arrays can be used in the same way that ordinary Riordan arrays can be used, using the same operation. And so because of that, we can actually compute the total number of short chords among our linear chord diagrams by taking our array, our exponential Riordan array, and multiplying it by the sequence of non-negative integers. I'll leave it as an exercise for you to confirm that the non-negative integers has a generating function of z times e to the z. And then when you perform the Riordan group operation, you end up with an exponential generating function that is essentially the same as the one we had for the total number of linear chord diagrams. So we're seeing here that the average number of chords of length 1 among all of our linear chord diagrams is 1. So that was sort of an unexpected appearance of the Riordan group again. And so I'll leave you with this final observation, which is that when you come across a result, such as the one I just quoted from the previous screen, it's really nice if you can come up with a bijective or combinatorial explanation or proof of that result. So in this case, what I said just a moment ago was that the number of short chords among our linear chord diagrams is the same as the total number of diagrams. So I'll just show you a really quick bijective proof of this, which appeared in our paper, the paper that Kendra and I wrote. So you take a short chord, which I've indicated here in black, in bold, and if you take the left endpoint of that chord and pull it out to the front of the diagram, you will get the linear chord diagram in blue below it. So I've illustrated that for these first 5 short chords. So I'll just let you stare at that for a moment. And then you can do that for all of the short chords that exist among your linear chord diagrams. So for every short chord, there is a linear chord diagram, and that correspondence is 1-to-1 and onto. So hope that you got something out of this lecture, learned something, or at least had a good time. I'll leave you with some closing thoughts. First, about the Riordan group. I'll just remind you that the Riordan group can be used to study, verify, and discover combinatorial statistics and identities. Every algebraic observation in the Riordan group deserves a nice combinatorial or bijective interpretation. Some words about the journey, mathematical or otherwise. First of all, there are many ways to go in the right direction. And along the way, whatever makes you feel most open, creative, and able to express yourself as your true self, that is worthy of effort, is worthy of attention and value, even if it's challenging. And the old adage is true. The journey is so much more than the destination. And finally, you can always go home, either figuratively or literally. So I just want to leave you with an acknowledgement of all the people who have contributed to my journey. Of course, I can't fit them all on this slide, but I've tried to identify my collaborators that I've worked with recently, including students whose contributions I've valued so much over these years. And you very rarely get a chance to thank your parents in public. So I want to take an opportunity to do that and thank my parents for setting me on the right path, and my siblings, my husband, my 3 kids, and my entire extended family. It's been a great journey. Thanks, everyone.
Thank you, Naiomi. That was really, really wonderful. It was really interesting mathematics, and I just really so appreciated the way you intertwined your professional and personal journey with the mathematical story. So thank you so much. That was really great. We will have a few minutes for a Q&A just momentarily, but before we get into that, I want to remind the attendees that because this is on YouTube, you or anybody else that you might know of who is interested in watching or rewatching this presentation will be able to find it on the MAA's YouTube page. And I also will mention that we are inviting the attendees to share feedback. Just a few minutes at any time to complete a short survey, which we will link in the chat. But now let's turn to the questions. And there were several that were already placed in the comments before the end of your talk. So we'll look at those, and then other folks can contribute questions as well. So yes, the first one is up, the inspiration for the Cameron Quanta identity.
Yeah. So I think the inspiration for that problem had to do with like generalizing Pascal's triangle. So the sum of the rows of Pascal's triangle giving you 2 to the n, so that classic binomial identity. The idea was to use the Riordan group to sort of come up with, sort of a bigger identity that applied to, generalized forms of Pascal's triangle. So there was sort of like a class of generalizations of Pascal's triangle that we were looking at, and then this identity kind of popped out of that.
Yeah, that's great. It would probably be interesting to spend a little more time even pursuing that kind of a question of how do you get inspiration? And when you I think your papers that you referenced were pretty much always with a collaborator, right? A single collaborator. So it'd be interesting to hear your thoughts on kind of how those partnerships evolve. But for now, we'll go on to, we have 2 other questions here. The first one is about determining if a Riordan array is invertible.
Yeah, so I kind of didn't go into a lot of details about the conditions on the generating functions G and F that determine the Riordan array. But as long as you put the right conditions on those, you can get an invertible Riordan array. And so for the most part, when you're dealing with the kinds of problems I was talking about, your array should be invertible.
Okay, thanks. And then there was another question also from Michael about other families of multivariate generating functions that can be, yeah.
Yeah. So, yeah, I mean, I think I've kind of gotten to this point now where, I said earlier that, the Fibonacci sequence is special, but it's not that special. That's kind of how I feel about the Riordan arrays also, so it's like, okay, it's just a geometric sequence of generating functions. But I sort of feel like, you could, as we did with the exponential Riordan arrays, sort of, there are ways to sort of adapt, the type of sequence of generating functions so that you do in fact get a group and then get some, interesting mileage out of that group structure. But the Riordan group is really nice, and I'm pretty familiar with it, so I like it and I use it a lot. It has inspired me, not always, but it has made me think about like one of the things I like about it is if you have an idea that something is true, or at least the kind of problems I think about, I can usually use the Riordan group to verify it, right? Like even if it isn't like the prettiest proof, it's like, okay, I can use a Riordan group to show that it's true. And then I can get to the part of like, that deeper combinatorial insight that we're often looking for.
Yeah, right. So so it's a useful tool. And I mean, your general comment early on about combinatorics kind of interacting with every area of mathematics. So the Riordan group is I think is a great example of that, right? I mean, you had a lot of different types of applications and illustrations that use the Riordan group, and it also really nicely illustrated the ways in which various objects within mathematics can sort of can simplify something that looks sort of complex and overwhelming, right? It can make it much more tractable. Let's see, there was another question here from Bruce Coletti about connection between the Riordan group and the unwound circle group.
No, not at all.
I'm not.
I'd love to know more. I have no idea.
Yeah, that's an intriguing question.
Yeah, I'll write a note to myself to.
Yeah, well, and maybe maybe that's a good place to sort of wrap up with that intriguing question. But thank you again so much, Naiomi. That was a really, really fascinating talk, and I appreciate it very much. Again, a reminder to everybody to join us again in 2 weeks when Dr. Ken Ono is going to be speaking to us. Dr. Ono is the Thomas Jefferson Professor of Mathematics at the University of Virginia, and he also has a little bit of an acting career, as it were. If you are Super Bowl fans, you may have seen him featured in a Miller Lite beer commercial. So join us again in 2 weeks for Dr. Ono's talk. Thank you all for joining us tonight.
Thank you.